In this video, I'm going through the key for the Monday-Wednesday section of the spring Monday-Wednesday sections quiz for spring 2020 quiz number 4. Now, the second standard on this quiz is dealing with antidifferentiation, differentiation, and motion with vector-valued functions. So basically, we're just reminding ourselves of this idea that if an object's motion is described by the vector-valued function r of t, so r of t is giving us position, as a function of time, then velocity is just the derivative of position. And speed, well, that's just the magnitude of velocity. Or if you prefer, the magnitude of r prime of t. It's represented by this Greek letter nu. It looks like a V, but it's a nu. And the acceleration of the particle traveling on the path with position given by the vector-valued function r of t, that's either the derivative of velocity or the second derivative of position. Now, on this quiz, I could give you position and ask you for velocity and acceleration. Also speed, we would have to take two derivatives, the first derivative and second derivative, to get velocity and acceleration. If I want speed, I just take the magnitude of r prime. Now, if I give you velocity and I asked you for position, well, then you'd have to take the antiderivative. Now, I'd also have to give you some initial position, some position at some time t, in order to get rid of all those constants of integration that come from taking antiderivatives. We don't want a position function with a bunch of arbitrary constants in it, because that's not going to give us a very good sense of position. I want to know what my position is exactly at a certain time. I don't want some arbitrary constant added to it. So I would have to take the antiderivative of v and then use some initial position or some specified position at a particular time t in order to find r. Now, if I give you velocity and I ask you for acceleration, you take its derivative. If I give you velocity and I ask for speed, you find its magnitude. Now, if I give you acceleration and I ask you for velocity or position, we antidifferentiate. So just think of it this way. If you want to go down, so you're going from position to velocity to acceleration, you differentiate. If you want to go up, you antidifferentiate. And you're going to have some initial positions and initial velocities to do that. But I can give you any one of these three and ask for the other two, and then of course speed is the magnitude of velocity in this standard. So this is the way I asked you about this particular standard this time. So I said, consider an object whose motion is described by the velocity vector. So v of t has these components: 4t times natural log of t times I hat plus 6t squared plus 4 times j hat plus e to the 1 over t all divided by t squared times k hat. And I'm asking you to find position, and I'm giving you some position at time t equals 1. So that's going to allow us to get rid of the constants. But if I have velocity and I'm trying to get position, I take the antiderivative. Because the antiderivative of velocity is position. And in order to take the antiderivative of a vector-valued function, you take the antiderivative component by component. So let's do the x component first. Generally, the way I write these, I try to include integration by parts and u-substitution and some basic rules. So you might have to brush up on that stuff. There are videos and practice problems on my website for Calculus 2 if you need to brush up on integration by parts. Now this one, this integral requires integration by parts. First, I notice basic rules don't work because I've got a product, and u-substitution doesn't work because I don't have any functions nested inside another function. You might say, well, t is a function. Yeah, well, if I let u equal t, then du equals dt, and I just end up changing all the t's to u's, and it doesn't help us. So I'm going to have to do something else. I have to use integration by parts. Now, when you studied integration by parts, you learned that you want to choose u to be part of this and dv to be everything else. And you want to choose u to be the function with the simplest derivative. And I told my students, unless there's a natural log of t or an inverse trig function, in those cases, u is the natural log or it's the inverse trig function. And we'll see why that's true in a second. So remembering that from Calculus 1, we say u is natural log of t, dv is everything else. I said Calculus 1, I meant Calculus 2, sorry. So I make my little 2 by 2 table. U goes there, du is going to go below it. dv goes over here, so that's everything else, and v goes above it. We're differentiating in this direction, and we're going to anti-differentiate in this direction. The derivative of natural log of t is 1 over t, then multiply by dt. The antiderivative of 4t, we add 1 to the exponent and divide by the new exponent. 4 divided by 2 is 2. That's our v. There would normally be a plus c there, but we leave it off whenever we're doing integration by parts. So the antiderivative of this is, according to integration by parts, uv minus the integral of v du. So as long as I always set up my 2 by 2 table this way, with u and v in the top row, and du and dv in the bottom row, it's always going to be multiply across the top, then multiply across this diagonal, and subtract the integral across that diagonal. So I have u times v minus the integral of v times du. Now be careful here. A lot of students want to just take the antiderivative of 2t squared and the antiderivative of 1 over t, and they give me 2/3 t cubed times natural log of t. That's not how this works. It's another product. So we've got to do something else. Notice that I could write this as itself over 1. And if I multiply straight across, I've got 2t squared divided by a t. Because of that, one of the t's is going to cancel out. It's a t times t divided by t. So one of the t's will reduce, and I'm just left with a 2t. So this becomes, I'm just thinking of this as scratch work. It's another line of reasoning. I'm still over here at the top. That is 2t squared, natural log of t, minus the integral of 2t. That's all that's left. The integral of 2t, I bring down my 2, add 1 to the exponent, divide by the new exponent, add a constant of integration. Since it's the x component, I'm going to call it c1. So we've got 2 more coming. So that is my x. 2t squared, natural log of t, minus t squared plus c1. Now for the y component, we want to anti-differentiate 6t squared plus 4 with respect to t. It's actually not too bad at all, just a power rule and a constant multiple rule. The antiderivative of this comes from bringing the 6 down, add 1 to the exponent, divide by the new exponent. Antiderivative of a constant is your constant times the variable of integration, which is 4t. Add a constant of integration, just call it c2. So this is going to give us 2t cubed plus 4t plus c2. All right. Now the z component looks a little tricky, but generally I give you u-sub, integration by parts, and basic rules. And those are pretty much the standard techniques. Everything else is derivative of that, using derivative in a different sense. Yeah, everything is either basic rules, u-sub, or integration by parts in some way with some algebraic manipulation. So I look at this and I say, do I have a basic rule for that? Absolutely not. It's a quotient. I do not have a quotient rule for antiderivatives. So don't do low, D, high, and all that jazz. That's not what's going on here. It either has to be a u-sub or an integration by parts. Now, I always try u-sub first. Basic rules don't work, try u-sub. Now, if u-sub works, u is usually the function nested inside another function, and I've got a 1 over t inside this exponential function. So I'm going to think of that as my potential u. So we'll call that t to the negative 1, and then compute its derivative. Now, we're never 100% sure this is going to work until we compute its derivative and see if it's up there somewhere. See if it is part of the integrand as a factor. So let's do that. So I have negative t to the negative 2. So I'm bringing my power down, multiply by t to the 1 less power. Don't forget to multiply by dt. And that looks a little different, but it's actually negative 1 over t squared dt, and I've got a 1 over t squared dt. The 1 is implied, that t squared in the denominator is a 1 over t squared. Represents a factor of 1 over t squared. So this is going to work, but I don't need the negative, so I'll multiply both sides by negative 1. Oops, that should be a dt, not a du. Okay, so we've got this. This is e to the u. 1 over t squared dt is negative du. Antiderivative of that is negative e to the u plus c. And I'm on my z component, so I'm going to call that z3. And just sort of saying that's a separate line of reasoning. This is equal to negative e to the u plus c3, and u is 1 over t, so we have to back substitute. All right. So we compute the antiderivative of the x, the y, and the z components. And this one required integration by parts. And that's just basic rules for y of t. And this one is just u-substitution. Now we've got our position function, but it has these arbitrary constants in it. We're going to do something about that. So let's put all of our pieces together. I'm going to use blue just to highlight the pieces. This is my x component. This is my y component. And this is my z component. So according to everything we've done so far, r of t is 2t squared natural log of t minus t squared plus c1 times I hat plus t cubed plus 4t plus c2 times j hat plus e to the negative 1 over t plus c3 times k hat. Now I don't want this version with all of the arbitrary constants in it, so I'm going to use the initial condition, that is the position at the particular time they gave me, to find c1, c2, and c3. So to do that, I have my r of t. So I have substituted the components that we just found into the form of r. And now we're going to evaluate all of this at t equals 1. And I'm using t equals 1 because they gave me r of 1. So remember, this is a t value. That's t naught, we often say. They call it an initial value because it's often t equals 0. We're saying, where's our position at time t equals 0? This time it's a little different. They're saying, what was our position at time t equals 1? And they're giving us this version over here. Now, they wrote it in terms of I hat, j hat, and k hat, so it's not in that component form that we've been using for the rest of the problem. There's no I hat here, so that's 0 times I hat. Then I've got 3 times j hat and negative e times k hat. So that's r of 1 in component form. So I'm going to use that here. Okay, so let's find r of 1 just using our formula. So I'm replacing all of the t's with 1. I'm going to use what I've heard described as placeholder notation. I'm replacing all the t's with 1s. Placeholder notation is just the exact same expression, but you put parentheses, open parentheses wherever you intend to plug in t, and then you just plug in t. It makes it really easy to see where t has been substituted and where it needs to be substituted. It often helps students when they're first learning how function notation. Okay, so we're here. This is r of 1, but it's got these arbitrary constants in it. So let's simplify it and then set it equal to the r of 1 that we were given. This r of 1, we were told that r of 1 has to be 0, 3, and negative e. And so natural log of 1 is 0, and that's just 1 squared, which is 1, times negative 1. So we get negative 1 plus c1 times I hat. That's 2 plus 4 is 6, plus c2 times j hat. And this is a negative e plus c3 times k hat. That is r of 1. In order to find c1, c2, and c3, let's set it equal to the r of 1 they gave us. They told us that r of 1 was 0, 3, and negative e. Now if that's the case, well then this x component on this side has to equal the x component on this side. And this y component has to equal the y component. And the z component has to equal the z component. Because the only way two vectors are equal is if their components are equal. So, with that in mind, I've got a system of 3 equations. Negative 1 plus c1 equals 0. And 6 plus c2, that has to be 3. And negative e plus c3 must be negative e. So if I solve this for c1, I get 1. If I solve this for c2, I get c2 is 3 minus 6, which is negative 3. And if I add e to both sides here, I get c3 equals 0. So you're not done yet. Once you have used r of 1 to find your c's, by first computing r of 1, setting that result equal to the vector that they gave you, and then solving for the c's, you've got to back substitute. You haven't found the position function yet. The final position function is this function here, where c1 is replaced with 1, c2 is replaced with negative 3, and c3 is replaced with 0. So we've got that. R of t equals this 2t squared natural log of t minus t squared plus c1, which is 1, times I hat plus t cubed plus 4t plus c2, which is negative 3, times j hat plus e, or negative e to the 1 over t plus c3, which is 0, times k hat. And that's our r of t. Now just for your notes, let me write down what we just did. We substituted the components that we just found into the form of r of t. Then since we were given, up here, we were given t naught equals 1, we evaluate that r of t at t equals 1. Oops, evaluate, I don't know why I put a line through that. Evaluate r of 1 and set that equal to the given r of 1, which was 0, 3, and negative e. Then you solve for c1, c2, and c3. That's what we did over here. You set the components equal to each other, you get this system of equations, you solve for the c's, and then you back substitute. So you're substituting c1, c2, and c3 into the form of r you had right here. So you're replacing this c1 with 1, and you're replacing this c2 with negative 3, and this c3 was replaced with 0, so I just didn't write anything. Okay, so that's all there is for that part. even though it did not seem like it, we're actually solving a differential equation. We had r prime equals this, and we have an initial condition r of 1 equals that. So we were getting rid of the derivative in that differential equation by taking the antiderivative. So this is a simple differential equation problem. If you haven't taken diffy yet, it's a little bit of a preview. Okay, now we're asked to find the acceleration function. Well, that's easy. Velocity was given to us. It had components 4t natural log of t, 6t squared plus 4, and e to the 1 over t all over t squared. And we're asked for acceleration. Well, acceleration is just the derivative of velocity. So we just need to take the derivatives of each of these guys, component by component. It's not too bad at all. Just have to remember our product rule, our quotient rule, or chain rule, and our power rules, and all those rules from Calculus 1. And remember, if there's any of that you don't remember, you can put that on your formula sheet, but we use it so often, it would be best if you could commit those to memory if you were very comfortable with them. You're going to have your formula sheet with you, so you can look at it if it makes you feel better. But ultimately, it would be best if you knew those by heart, so you didn't have to take a long time to work out a derivative. Okay, so I've got this right here for my x component. Well, that's a product. I've got a 4t next to a natural log of t. So that's my first function and that's my second function, so I'm going to use a product rule for that. Well, that's just a constant multiple rule and a power rule, and the derivative of a constant is 0. So that's just some basic rules. And here I've got a function divided by a function, so that's going to require the quotient rule. Now we could do all three of these in line within the vector, but I think that makes the work look a little messy, so I'm going to do that outside of the vector. So let's just do one component at a time. The x component is the derivative of 4t times natural log of t. This is my first function, and this is my second function. We get derivative of the first times the second plus derivative of the second times the first. You may have memorized that in the reverse order. That's okay. We just need to differentiate one, multiply by the other, then do it the other way around, and then add them. Okay, and then we just evaluate those two derivatives. Derivative of 4t is 4. Derivative of natural log of t is 1 over t. So we've got 4 natural log of t plus 1 over t times 4t. There's an implied 1 down there. Those t's are in the numerator and denominator, so they reduce, and you just get a 4 natural log of t plus 4. You can factor out the 4 if you want to, but it's not necessary. Alright, so that's our x component. Y component is very simple. I've got a constant times a function of t, an explicit function of t. So I bring my constant down, and then I take the derivative of t squared. So bring my power down, multiply by t to the 1 less power. 2 minus 1 is 1. The derivative of a constant is 0. So that simplifies to 12t. It's my y component. The z component is the most complicated, complex of the three components. Notice we've got a quotient, so we're going to have to use the quotient rule. Now, Now, this is the mnemonic I was taught in high school, AP Calculus. This is the high function and this is the low function. According to the mnemonic, it's low d high. So we do t squared times the derivative of the high function. And this is e raised to the 1 over t. Now we could leave it like that, but 1 over t is really t to the negative 1. I'm going to write it this way because it will be easier to take the derivative of later. So I have low d high. D high is derivative of high, derivative of the top function, minus high d low. And if you want, you could do these derivatives as you go. I'm choosing not to. I'm choosing to use the quotient rule first, and then I write all my derivatives in red to tell me that's more work that needs to be done right there. So that's low d high minus high d low over low low. It's t squared squared. T squared squared is t to the 4th. Got a t squared right here. Now this requires the chain rule because I've got a function inside another function. The derivative of e to some power is e to that power times the derivative of the inside by the chain rule. Now the derivative of the inside is negative t to the negative 2, and that's it. So we have exactly the same exponential times the derivative of the inside, and that's right there. This guy just comes down. Derivative of t squared is 2t. And remember how exponents work. If you have t to some power times t to a different power, you add the exponents. T to the 2 or second times t to the negative second. I do 2 plus negative 2 is t to the 0, so that's just a 1. So these guys reduce. And we have e to the 1 over t times the negative 1 minus 2t e to the 1 over t all over t to the 4th. You could factor out the e to the 1 over t or the negative, or you could split this into two terms. It's up to you. Or you can just leave it alone. I'm going to leave it alone. And then just put all your pieces together in your acceleration vector. So I need the derivative of the x component, which was right here, times I hat, plus the derivative of the y component, which is right there, times j hat, plus the derivative of the z component, times k hat, and those are just the three parts that I'm going to list in my vector. So I've got 4 natural log of t plus 4 times I hat, plus 2t times j hat, plus negative e to the 1 over t minus 2t times e to the 1 over t all over t to the 4th times k hat. And that's it. That's our acceleration vector. Now, some students are going to make some mistakes with simplification. It's very tempting to take that t squared and that t to the 4th and just cancel that t squared immediately. That doesn't work that way because of that minus sign. We only get to cancel that t squared if it's a factor to both of these terms. And after simplification, it wasn't. There weren't any t's to any power over here. So we're done. All right, guys, if you do the reassessment over this, I might not give you the velocity. I might give you the acceleration and an initial velocity and an initial position and ask you for the velocity and position. I might give you the position and ask you for the velocity and acceleration. It would require differentiating twice. I could also ask for the speed. I could ask for the jerk. There's a lot of things I could ask for. So make sure that you're prepared for those. It's going to require a lot of review of differentiation and anti-differentiation rules. All of them you can put on your sheet, but you need to know how to do it and do it relatively quickly. It shouldn't take us 30 minutes to do a derivative. It's a very standard skill that we're going to use over and over and over again throughout calculus and differential equations and in engineering analysis and all of those classes that you're going to be taking in 3,000 level classes. Most of you will be taking at OSU. So remember these relationships and remember how antiderivatives and derivatives work.